to tell you about the mathematical modeling. So mathematical modeling is a discipline that attempts to describe real world phenomena in mathematical terms and then solve them. Even you and we know and understand that if you want to deal some real world problems, so if you want to deal with the experiment works, so it is very difficult and could be some costly, so that's why we apply our mathematical modeling phenomena. We actually understand the real scenarios and some like parameters what explains such kind of phenomena, and then we apply our mathematic assumptions to model such kind of models. So in this diagram you can understand, so if there is some real world problem, then we can model some real world model based on some assumptions, and of course those assumptions will be the mathematical terms, and we will use some symbolic calculations, symbolic things like variables or constants in the purpose of the model, and then we propose a mathematical model. And now we have some model based on the real world application, but thing is that we have the model, but nobody wants the model, everybody wants the solution, because if there is a problem, then we have to find the solution. So that's why mathematics known for that. So we provide solution. That's why when we have the mathematical model, so based on our some mathematical tools, dynamical tools, numerical simulations, or some mathematical experiments, we have some conclusions on the real world application, and then we can conclude that result, and finally we can compare with the real world application that it matches with the result or the scenarios or not. So that's how the mathematical modeling works. For example, in my case, actually, I'm working on mathematical models in ecological systems. So I started working mathematical model from the one species model. So as you can see in this slide, so this is a single species model. Like there is some population and how population grows with some mathematical assumptions. So this was the first mathematical model proposed by Malthus. So we also call it Malthus model or the exponential growth model. So here the assumption of the population grows was that the rate of the growth of population is proportional to the population present at that instant. So that's why dn by dt, it's a rate of growth of the population, and it will be directly proportional to its population like n. So that's why if we remove the approximate this proportional sign, then we have some constant parameter r, and we call it intrinsic growth rate. And of course, we can treat it like birth minus death, of course, and even more parameters can be assumed like immigration or migration, something like that. So this model is proposed with the equation number 2 and could be solved with the positive initial conditions. Initial data, of course, would be positive because here we are dealing with the population, so n naught is a positive parameter. And of course, when we solve this kind of equation number 2, this is a separation of variable type of model, and you can easily solve it by separating n and t from both sides, and you can easily find the solution. So we have the solution like in the form of exponential, as you can see in the equation number 3. And if we plot with some n naught, so you can see here in this diagram shown in the right side, so this is n naught is the initial population, and it will increase if your r is positive and decrease exponentially when r is negative. So in the both scenario, we can understand this population will increase exponential or decrease exponential. So this was the first mathematical assumption that someone, Malthus, he assumed that the population grows exponentially. So that's why this kind of scenario occurred. But most of the people, they are not happy with that model, because they know nothing is in this world is like this that will grow exponentially. There will be certain limitation on then, or of course that population will die somewhere. So there should be some decrease also in this population. So that's why in that market, the second model came, and that was the logistic growth model, as you can see in this equation number 4. So dn by dt equal to rn 1 minus n by k term. So there was some limitation term, as you can see here, 1 minus n by k, which shows that the population should be always less than k, where k is the carrying capacity parameter, which shows that the population individuals can maximum increase that level where the environment can support. So in this diagram, you can see we can show this phenomena like this S-type shape curve or sigmoid curve, we can say. So like if population increasing, then that will go to K, maximum K level. And if we start initial from the upper than K, then it will decrease to the K. That means K is the very important factor or the carrying capacity parameter where the population goes. Either it will decrease or increase or decrease to that level. So that was the realistic scenario actually, because we do not have that much resources that any population can survive exponentially in the environment. So that's why there should be some limitation. So that was the limitation model proposed in 1838 by Wurst. So this model is called logistic growth model. So this is the second single species model. However, in the biological populations, there are so many single equations or single species models you can see. Like if we see that there is a model with the harvesting, or some model with the constant rate harvesting, there is some model with the LE effect. I'm not going that much biological terms, but I'm just showing you how these kind of model proposed and how these equations look like. And the third equation is model with LE effect, and the last there is a LE effect and harvesting both. So if anyone want to propose single species model, so they can consider some ecological factors like harvesting or some LE effect phenomena, or maybe they can add some other ecological factors in their model, and they can propose single species model. So this is all about the single species models. Then we will move to our two species models, because you know the world is not enough without the interaction. So there should be some two population at least. So that's why we move for a prey predator model. So this is a two species prey predator model. You can see here. Prey predator means the predator kills and consume prey to survive in the environment. So it shows some kind of interaction between them. So it is a good model that comes in 1925 with the Lotka and Volterra model. As you can see here in the equation number 10, this is the model where P is the prey population, Z is the predator population. And these equations or systems show how these populations interact. So if I talk about the first equation, you can see here in this first equation, A1 is the like birth rate, as we have seen the last single species equation. But there is some decrease in the population involved, like B1 ZP. So B1 is like work like a predation rate or total killing rate by predator. So there should be some decrement in this population growth. And if predator population consume prey, then of course it impacts the biomass of the predator also. That's why due to this B1 ZP term, so there should be increment in the Z population, that means the predator population. So as you can see here in the second equation, we have B2 ZP. So this is a biomass conversion, like predator eating prey, and this biomass converted into predator. So it works like a growth. And of course, there should be some death rate. So there is a death rate A2 for the predator population. So this was the first prey predator model. We can say it is a classical prey predator model proposed by Lotka and Volterra in 1925. If I talk about some examples, you know very well the examples of prey predator, like you can see in the diagram. There should be rabbit treated as a prey, and there should be some there should be tiger treated as predator. Or in the aquatic environment, you can see there are some big fishes and they are eating some small fishes. So we know everywhere and we can see everywhere the prey predator interactions things. So this is a first two species model, and when time passes through, and then many models came in the market. So then there was a second model you can see here in this equation number 11, and we call it Rosenvik-Markothel model, RM model. And in this model, there was some speciality in the predator population was because the predator population was the specialist predator. We call it a specialist predator because it dies out due to its favorite food, in the absence of its favorite food on short supply. That's why in the second equation, we have assumed this minus A2Z term. That means it death due to this favorite food. So otherwise, other parameters or other things are same, you can see here. And the second thing was changed that here in this model 10, you can see here there was the interaction B1 ZP, but it's changed to here in the rational function, you can see here. So this rational function was the Howling type second functional response. I will talk about later about the functional response. So it shows the interaction between prey and predator with some functions, and it could be some linear functions, some rational functions of different forms, or some exponential function. We will discuss about it. But in this model, the specialty was that the predator was the specialist predator, JIIT population. So that's why this kind of equation forms, or the system forms. So this is the second equation of the two species model. And of course, now we have the third type of two species model, which we call it a Howling-Tanner model. So there was the specialty was that in this equation, you can see here there is a JIIT population, which is your predator population, that was not a specialist. Now this time it was journalist. A journalist predator are different from a specialist predator because they do not die out due to its favorite food. Maybe they can survive with some alternative options available in the forest or somewhere. So this is a different kind of predator population. We call it journalist predator. And due to this, we have this kind of form you can see here in the second equation. There is no death rate, natural death rate due to its absence of favorite food. There should be some increment, some linear increment, CZ term, and there should be some decrement due to its own population, due to competition, and this shows some other kind of behavior from the specialist one. So this is your journalist predator. So of course we have different kind of model, and we call it prey journalist predator model. The difference is that here we have the specialist predator, but here we have the journalist predator. And of course, we can see some examples like foxes, cats, common buzzards, hooded crows, etc. As a journalist predators. And similarly, we can see examples of specialist predator like hawk, owl, least weasel, stoat, etc. So these two are the so first, second, and third. These three are the two species models. And of course, we can have some general predator model. Of course, if you want to propose some new model, then you can propose by your own. So how you can propose, like we have two equations, like first equation of equation number 13, like dp by dt equal to rp, where rp works like a growth function. It's a growth function. You can take different kind of growths, like we have some linear growth, we have logistic growth, we have Smith growth functions. So we can use the growth functions here. And the second is fpz. So this term is the functional response. So what is that? A functional response, or the trophic function of the predator to the prey density in population dynamics. It's referred to the change in the density of prey required per predator in unit time as the prey density changes. That means somehow it shows how the predation rates happens, or how the this interaction working. So this shows the relationship between prey and predator populations, as you can see in this diagram. So we have different kind of functional responses. I will talk about it in the next page. And similarly, due to this predation, we have some growth in the population. So this is the growth in the population Z. And of course, there is some death involved for this predator population, that you can take death parameter, some constant parameter, or you can take some function Z due to its intra-specific competition. So based on these functions, you can make your general predator model, your some predator model. So it is very easy task to create some predator model. You can create your own. So in this diagram, I have shown some functional responses which are famous in this biological phenomena, like Howling type first functional response, which behaves like linear one. You can see in this diagram. So basically, it shows the number of prey consumed versus density of prey population in the relation between them. And some second, the Howling type second functional response, which treats like cytoid. As you can see here, this is your Howling type 2 functional response, a rational function. And if this curves work like this, and the third one is the Howling type third, and it works like this. First of all, it will increase and decrease to that level. So basically, there are so many kind of functional responses, as you can see here in this diagram. So if you like it, maybe you can take some screenshot or picture of that, or I will share the slides later. So these are some functional responses that you can use in this general predator model, and you can create your own population model. But you have to take care of the biological terms, the biological phenomena, that these species either they are following such kind of interactions or not. So you have to make sure of it. Then you can propose the new mathematical model. So these are the two species food chain models that we have discussed yet. And now we are moving to three species food chain models, three species models. Three means understand very well, because since in the first species there was only one population X, in the two species there were two populations X and Y, and now in the three species model there would be three populations X, Y, and Z. So here I am talking about some food chain model or food web model. These are the applications of these such kind of models. So if you can understand from the diagram, so in the left you can see here it's a food chain. Because there is some primary producer, then there is some uh, uh, locust like primary consumer, then there is lizard as a secondary consumer, and snake as a tertiary consumer. So basically they are making a food chain, and there is a single resource line. You can see here, because there is a single resource line. The difference between these food chain and food web is that depends on the energy line. You can see here. In the right side, it's a food web. Here, as you can see here, the snake population, it taking energy from different resources, like from lizard, from frog, from mouse. So maybe if you want to make a model, then if X is the mouse population, Y is the lizard, frog is the Z population, and snake is the W, then you have to take the interaction with all these two, with the XW, YW, ZW, because snake can eat these three, right? So that would be more complicated actually. So it's called a food web model. But here I'm talking about food chain model, because in my research work, basically I work on food chain model where the single energy source belongs. For example, if I'm showing you an example of a food chain model. So since if we deal with the two species models, then if I talk about the specialty, what is what is in the three species model, so there is chaos. I will talk about the chaos later. Chaos actually it's a very good phenomena that occurs in at least three species model. Since we are dealing with the continuous model, so there should be three population at least for to obtaining chaos in our system. So this was the first chaotic model proposed in 1991 with the Hastings and Powell. So there were three populations, X, Y, and Z. And you can see here, Y survives on X population and Z survive on Y population. There is no connection between Z and X. So if there is connection, then it would be food web, not food chain. So single energy source line we can see here between these species. So based on some assumption, they propose the model. For example, in the X population, that means X is the prey population, which comes in like primary producer population. Like, so it grows logistically, as you can see here, K naught is the carrying capacity parameter, and it interacts with the Y population with the hauling type second functional response. You can take one if you want. And according to that, we have some growth in the population. Then again, this Y population, interact with the Z population, and then it has the natural death rate D1. So the thing is that you can see here the middle predator population uh, dies out due to its favorite food. So it's a specialist predator. That means our middle predator is a specialist. And similarly, we can see here our top predator population is also a specialist. I have already discussed the specialist and generalist predator population models. So basically, this Hastings and Powell food chain model, it was the prey specialist middle predator and specialist top predator model. That means Y and Z both populations, predator populations, are kind of specialist type. So this is a food chain model. So Hastings and Powell, they observed chaos in the system. So you can see here there is a chaotic attractor. So this is the specialty of the food chain models. There is a possibility you can obtain some chaotic attractors or the chaos in the food chain models. And if you want, you can control or you can detect them. So I'm just showing you the example, not discussing everything in detail. The second model came with the Upadhyay and Rai model. And here they assume the similar assumptions for the equation number 1, equation number 2. But there was a different assumption for the equation number 3. As you can see here in the third population was journalist predator. Like they are not dying out due to its favorite food, middle predator, they just alter themselves or survive themselves with the different alternative options. So that was the major difference between these two models. And of course, it was first a chaotic model, and it has been seen in 1997 after the Hastings and Powell model. So these two models was very popular in the past decades. People are controlling these two in these two models. People are working. They are applying some different uh, ecological factors or some like synchronizations or some control parameters to control these kind of chaotic dynamics. So I'm just showing you the examples or the how we can model these differential equations to model some real world phenomena. And if I talk about the general food chain models, so you can see here I have taken the specialist middle predator and specialist top predator model. Of course, similar with the Hastings and Powell model, where X is the prey, Y is the middle predator, Z is the top predator. And of course, you can take F1X or F2Y like functional responses with the different one. Like you can take with the table, like you can take some linear functional response if you want. Yeah, either you can take the Holding type second or Holding type third. So even you can find most of the work like this. People they are using researchers. They are using different functional responses, and they are controlling this chaotic dynamics with some different ecological factors. So that's how this three species food chain models proposed. So I have shown you the single species models, two species models, and three species models. These are the models. So if you want to propose a new one, maybe these are very helpful to you. Maybe you can propose some new one with these. Now we are moving to some nonlinear dynamics that occurs in such kind of systems. So since I'm talking about models, so maybe I'm not talking about that much about the theoretical part, but maybe I will include some parts about that, the nonlinear dynamics. So there is a fixed point. So if I talk about the fixed point, since we have the system like x dot equal to fx type, as we have seen in the left side, there is a, uh, I just listen, there is some message. Should I continue?
Sir, your PPT not visible.
Not visible.
Yeah. Yes.
No, it was visible. I was just checking the message. Maybe someone
Okay.
text me, so that's why.
No.
So that will be helpful if you read out me in the land. So that will be nice. So these are the models. Now I was talking about the nonlinear dynamics in from the theoretical point of view. So we have a fixed point. Actually, fixed point we can say equilibrium point, rest point, stationary point. These are the common words for the fixed point. So since we are dealing the real world problems, so it is not easy to find the exact solutions of these systems. Maybe you can find with some doing research or something else, but as I know, these are the very nonlinear systems. They are rational functions, and rational functions are very complicated to deal with. So it is not easy to find the exact solution. So that's why we apply our dynamical approaches here. So we call it dynamical tools, dynamical systems, because we are dealing with the time. So there is a concept of fixed point. So if you take right side fx as a 0, then you have x dot as 0. So you are able to find some values of x for which fx equal to 0. We call it fixed point. And in the dynamics point of view, we have two kind of fixed points, like stable fixed point or unstable fixed point. So here you can see in this fixed point, there is a stable fixed point. That means if you solve the model in numerically, like for example, if you solve the model numerically, then maybe you are taking some initial condition in the 2D diagram. So that means that trajectory will start from there, right? And that depends how it trajectory goes. So basically, stable fixed point works like a sink. So if you have some direction fields just in the surround of that fixed point, like the dot you can see here in the diagram A. So these trajectories come towards to the fixed point. You can take fixed point from anywhere. If you are taking anywhere in the domain, that will be globally stable. And if you are taking in the surrounding of that fixed point, in the neighborhood of the fixed point, then that would be the local stability. So in the stable case, we have a sink, like these trajectories converge to the fixed point. So this is called your stable fixed point. And the second dynamic is unstable fixed point. Like if we are taking the initial point in the neighborhood, and this and the trajectories corresponding to that point will diverge out. That means it do not converge to the fixed point. It will diverge from the fixed point. It will go somewhere else. So such kind of scenario we have seen like a source. Like there is a point, and of course things are going on far from the source. So this is a source kind of figure, we can say. So in the second diagram B, it's a unstable fixed point. So if you want to calculate the fixed point, you can follow this mathematical calculation of phenomena. There are some 10 theory behind that, but I'm not discussing that much in the depth. I'm just giving you some idea about it. And the second dynamic that occurs in such kind of system is a limit cycle. So if you are having a single species model, so maybe there is a possibility you can get a fixed point dynamic. But for the limit cycle population, at least you should have two species, because if they are interacting, then such kind of phenomenon occurs in the system. If I talk about in the physical point of view, so stability means always when we increase the time, then of course the population fluctuations will come to the equilibrium always. But it is not that much realistic in our real world scenario. In our real world, there should be some limit cycle. That means there should be some ups and downs from the dynamic point of view, and that would be more realistic. So that's why this is the second phenomena, limit cycle oscillation. And of course, when we calculate, when we solve two equations like World-Lotka-Volterra system or some other two species models, so we have these kind of phenomena like stable limit cycles, unstable limit cycles, or semi-stable limit cycles. So let me clear with that one. So what is a stable one, what is unstable one? So for example, if you are having a stable fixed point, a fixed point, not a stable, a fixed point which is unstable, which means the trajectories will goes away from the fixed point, but that trajectory will converge to some cycle around that. You can see here there is some cycle here in between that. So trajectories from inwards, it going to this cycle, right? From one side you have checked. Now I'm taking the initial condition just outside of the cycle, and again the trajectory is going to the cycle. That means trajectories are going to the cycle from outwards or from inwards, from both sides. So these kind of cycles, if you are getting, or the orbit you are getting, it is a stable limit cycle. But what happened when it fails from somewhere, maybe from the outside, maybe some from the inside? So if it fails from one side only, like from outside or inside, so it's called semi-stable limit cycle, as you can see here in the diagram C and D. In the diagram C, you can see here on CD, a semi-stable diagram. There should be some limit cycle where this trajectory goes, but as we are observing, the inside the trajectories are coming to the fixed point, and from the outside converging to the limit cycle. So from one side it is working like a stable limit cycle, so it's a semi-stable. And similarly in the D diagram, you can see here the trajectories are diverging from the inside, but yeah, they are diverging from the outside and they are coming to the inside. No, they are diverging from outside. Okay, this is a different diagram. So if from one side it is converting to the limit cycle, this is your semi-stable, and in the unstable, it diverging from both sides. Like from the inside, it is diverging, from the outside, it is diverging. So in the diagram B, you can see here, uh, it's diverging from the limit cycle, of course, and from the outside, it is also diverging from the limit cycle. So in the figure B, it is an unstable limit cycle. So you will observe such kind of dynamics when you solve these food chain models or prey-predator models, two species models. You will observe such kind of dynamics. So now I am going to talk about Hopf bifurcation. So when you increasing one by one from the dynamics point of view. So first it was the stable fixed point, then we have seen the limit cycle. So since there could be some parameters involved in the dynamical system or the model, when you increase that parameter, then these dynamics changes. Maybe first time you are getting the limit cycle appear, and again you are having a when you increase the parameter. And similarly, if you have the fixed point and when you increasing the parameter, maybe you have the limit cycle. As you can see here in this diagram, there was first time it was the in the first portrait you can see first time it was the stable. Then you can see here there some orbits. It's like creating orbits like when we increase the parameter. That means the fixed point it's completely destroyed, and there is a birth of the periodic oscillation. That means the limit cycle. So if there is some scenario where we increase the parameter, a single parameter, one parameter bifurcation, a bifurcation parameter, and we see that there is some local birth or death of periodic solutions. So such kind of phenomena we call it Hopf bifurcation. So when you working two species model, not in a single species, if you are working two species model at least, then you are able to observe such kind of dynamics. You can observe their Hopf bifurcation. Even there are so many other bifurcation exist in the studies. You can also see those bifurcations, but this is a very important one. That's why I'm talking about this Hopf bifurcation. Now there is a period doubling bifurcation. Since in the limit cycle we have oscillation with a single cycle, but what happened with the if this cycle changes and it becomes the double of the previous one? So this is your period doubling bifurcation. This is a limit cycle diagram. In the end, you can see a periodic oscillation of the period cycle with the single um, period, but here two period exist for this diagram. So this is a period doubling bifurcation. Why I'm talking about this? Because basically you have to approach the chaotic dynamics. So if you want to approach the chaotic dynamics or the nonlinear dynamics, so you have to understand one by one how these phenomena changes. First of all, you are having the fixed point stable dynamics. Then you have the limit cycle oscillations. So between them, you have a Hopf bifurcation. Now you again increasing the parameter. Then you are having the period doubling bifurcation. Now again you are increasing. Now you have the period doubling route to chaos. As you can see in there in this diagram, first in the 2D diagram or 3D diagram, we have shown the phase portraits, and those are similar. In the first diagram, you can see here there is a stable focus. We call it a stable fixed point. That means all the trajectory converges to the fixed points, like sync phenomena. So when you increase the parameter in some model, so you are having a limit cycle oscillation, here, as you can see in the second diagram. In the third diagram, you are seeing this as a period doubling, and in the end, you are observing the chaotic effect. So that's how you can see these. Maybe I will show you with the animation. Let's wait, it's playing. So I think it is visible to you. I'm playing this animation. So maybe there is some A naught parameter involved. So there is a fixed point. You can see here, which is a stable fixed point. And now it's changing to the orbits, the periodic orbits. Yes, now it's changing to periodic orbits. So it's a single periodic orbit, which is a limit cycle, but now it's break into two cycles. You can see here. Yeah, it's breaking to two cycles now, in 4 cycles, in 8 cycles, and eventually it's having so many to broke up in this with us many cycles. So this is a chaotic attractor actually. So if you are obtaining such kind of scenarios, so maybe you are getting a chaos in your system, and of course for that at least you have to solve the 3 species model. I'm not discussing that much in detail, but if you talk about the Poincare-Bendixson theorem, so according to that, you can only have the fixed point or the limit cycle in the 2 species models. There is no possibility of getting chaos in 2 species models. So at least if you want to obtain chaos in your system, so you have to deal with the at least 3 species food chain models. So that's why I have shown you 2 chaotic models. Those were the 3 species food chain models. Now I'm going to talk about the reaction diffusion system. In the last these models, as we talked about, these are the ODE models. As you have seen, there was the ordinary derivative involved, and in the right side we have the reaction functions. So this was the ODE model, but in the ODE model we have only considered the like time as a can move also in the space. So that's why we are also considering one of the second independent factor, which is our space, small x or small y. That could be, that depends. If I'm talking about the one-dimensional space, then I can take only one variable x. And if I'm taking two-dimensional like a reason, so I can take x and y both as an independent parameter. So basically this, of course, you know, when independent parameters increases, you are just changing your model to from ODE to PD. Now this is a PD model. So I'm just talking about the two species model. In the left, you can see here the derivative where with the time, and in the right side, you can see here there is the reaction term, which is quite similar to the models that we have studied earlier. The thing is that two things are changed here. First of all, the derivative is now partial. In the right side, you can see here this term. This is a Laplacian operator. And this Laplacian operator could be like this in one dimensional and could be like this in two dimensional. So if you want to understand the theory behind it, reaction diffusion theory, then you have to find at least a diffusion model. You have to find a single species or single diffusion models, how it works. So you can see here that if you take some rod or you will heat it like heat equation works, heat or diffusion equations are quite similar. You can easily understand. And D1, D2 are here diffusive parameters, like how they diffuse, how at which rate they are diffusing. So like you and we are both populations, and if they are living in the some forest, and then maybe there would be some interaction between them. There are some if tragedy happens, then how they are interacting and how they are distributing themselves in the domain. So like this, you are just observing the arrangements of these species in a spatial domain, how they are moving. So this kind of phenomena comes with the reaction diffusion system. So this is a very general model. Here, if you the G in that model. And this model will be solved with the positive initial condition at time t equal to 0. In the equation number 19, you can see. And we have taken the third equation, the Newman boundary condition here, and which is called the zero flux boundary condition, which means no population will go outside and taken this general model, which is called the reaction diffusion model. And these are the examples of these. In the starting, I have shown you these two OD models, and of course now I'm showing you PD version of these two models. You can see here. So the OD model, if you change this just into D, so this is your OD model, and you have to remove these Laplacian operators, right? So the OD model, this is the, I think this is the specialist one, specialist model, and this is the generalist model, right? So I'm just adding the reaction diffusion theory here. So based on Turing instability, we have some assumptions. So this is the proposed model. So if you want to propose a new one, even in the two species, even in the three species, so you can just change this derivative and you can just take this Laplacians and you can make your own model. So I'm just giving you an idea, not just a detail of it. So maybe you can starting study of these kind of works. So these are some examples of reaction diffusion models. So actually in the reaction diffusion models, there is a theory, we call it Turing instability theory. In the Turing instability, if these two populations interact with the different diffusive rates, if D1, D1 and D1 and D2, those are not equal. So maybe at somewhere they have an interaction like Turing instability occurs, like our stable fixed point becomes unstable due to diffusion, right? That means in the absence of diffusion, the model was stable, but when you are considering the diffusion, this model, the steady state becomes unstable due to this diffusion term. So we call it Turing instability. And based on that, if you calculate the spatial domains, how the pattern formation or the patches works, so you can obtain these diagrams. In the right side, this diagram is for one dimensional. You can see here X is the space, T is the time. In the left side, you can see here, this is a snapshot of 2 dimension. Here, two space, X and Y are involved. So basically here, red color shows the high density and the blue one shows the low density. So in this diagram, you can observe that how these population are distributed or how they make some arrangements when time increases. So these patterns you can get in the Turing stability theory. So maybe if you want to, you can start a work on pattern formation theory. For your interest, I will show you some animation as I have shown you for the OD model. So this is an animation for PD model. So this shows how this snapshot. I'm increasing time. Yes, now when I increase the time at above the 1500, you can see now the patterns are started forming. You can see the patterns. So now you can see here some patches, some hot spot patches. So these are the red, maybe patches, the red patches. These are the high density patches, and where the blue color shows the low density low density. So this arrangement, as you can observe, time for different parameters. So here basically I'm increasing the time and you can start a pattern. Was the stationary patterns because it almost started almost fixed due to after some time, but this is a non-stationary patterns because it never stopped. When you increase the time, it always changes their positions, their arrangements. So this is a non-stationary patterns. So basically, there are two kind of patterns like Turing patterns, non-Turing patterns, and there are so many theories and phenomena involved those kind of areas. So if you just want to work on the diffusion models, so you have to deal with the pattern formation, Turing instability models. So these kind of works are very interesting. Even there are so many kind of diffusion phenomena like cross diffusion, or maybe you can use some Texas models. So there are so many kind of diffusions you can use. So there's a lot of work to do in this direction. So if you want to, you can do that. So this is just a simulation. Now I'm just about to finish the slide. So now I'm talking about the simulation tools that I have used to simulate such models. So in the MATLAB, actually, I have done all kind of simulations. So if I want to solve the OD models that I discussed, like single species model, two species model, three species models, so maybe you can use the OD45 solver in the MATLAB. It is it is built up code in the MATLAB. You can easily find on the internet searching OD45 solver, and you can see that they have solved some 3 systems or 2 systems with the OD45 solver, and then you can solve your own system with that. So this is a OD45 solver. And if you want to solve the PD system, then there is a package which is called PDPE solver in the MATLAB. So you can easily solve one-dimensional system of equations or PDs easily with that PDPE models. Solvers. Then there is a 3, which is a matcont. You can see here matcont. So if you want to observe the dynamics of the OD model with detailed analysis, so you can use matcont. There's a package, you have to just install it in your MATLAB, then you can use matcont. So you can plot different kind of diagrams, you can detect chaos, you can detect bifurcations, you can plot the direction fields, or many kind of time series and other diagrams with the matcont. And auto also work with the same. You can also solve with the auto. Auto is just software. It's a completely different software. You can install it and understand how you can use that. You can understand the dynamics of the OD model. Dynamic solver is also a software. You can also use that one. And you can plot the bifurcation. And to work in a chaos. So it is a very important tool. Maybe you can use E and F chaos. You can calculate the Lyapunov exponents, phase diagrams, time series, even the basin of attractions, many kind of things which are used to detect chaos in a system. So you can use those in this software. And the 7th one, the last one, is the Mathematica. So I'm not using that much Mathematica, but if I want to do some symbolic calculations, like if I want to understand the determinant of the matrix or some roots of the cubic equation, or sorry, quartic equation. So they are very difficult to analyze in some manner. So for that purpose, I use Mathematica for the symbolic calculations. So that depends. You can use those one. And the last, I would like to refer you for some books. These are the references books that I have used during my study in my PhDs, and still I'm using those. So these are the reference books. First of all, it's the Mathematical Biology by J.D. Murray. So you can use J.D. Murray book. There's a 2 volumes of this book. One is related to some ODE models. Second one is with the PD models. So there's a 2 volumes of the Mathematical Biology book by J.D. Murray. Even you can find the lecture of J.D. Murray on YouTube. So there is a J.D. Murray book, first one. Second one is the Mathematical Ecology by Mark Cote. So you can also use this book, Mark Cote, where you can find some models, ecological models. There are certain bit analysis, chaos. You can easily understand the things because this book is very readable and very easy to understand. So you can follow this book. Third one is the Nonlinear Dynamics and Chaos. So this book is very good. If you even you can find the lecture of Professor Stroh. So Nonlinear Dynamics and Chaos will give you one in celestial mechanics or space dynamic models. So you can go through this book. Fourth one is this is a book by Upadhyaya and Inger. And if you want to understand the ecological models, chaotic dynamics, you can go through with this book. And the fifth book is the Spatial Patterns in Ecology and Epidemiology. So if you want to understand the pattern formation, so there are 2 books, the fifth one and the seventh one, Spatial Dynamics and Pattern Formation. These 2 books you can follow if you want to work on PD models. And if you want to understand the theoretical point of view that how we calculate the stability, how we do analysis. So for that purpose, you can use this book, Stephen Wiggins' book, and the sixth one, the yellow one, this one. So this is a Stephen Wing's book. So you can easily follow this and you can understand theoretical point of view. This is a very nice book, in my opinion. You can see that. So first, if you are first time going to simulate the ODE models or going to simulate the preparator models, so you can use this book. This is a very nice book, Dynamical System with Application. Lynch is very good. You can easily find there some MATLAB codes, and they have solved the ODE systems with OD45 solver, and they have provided some diagrams, even different codes for the different scenarios. So this is a completely related to if you want to understand or learn simulation for the OD models, then you can go through this book, The Dynamical System with Application with Stephen Lynch. This is a very nice book. So this is all about I talked about. So thank you very much.
Thank you, sir. Thank you very much. Any question from audience?
Yes, sir.
Yes.
Sir, very nice presentation. Sir, can you explain some, sorry, can you give some idea about how you did that animation in 2 of your slides?
I did this animation in the MATLAB. Actually, I'm in the MATLAB. There is some like movie type packages I can use. So that's why it took some snapshots with the time interval, like maybe for the time like t is equal to 0 to 15 or 15 to 30. That depends on you. So in some intervals, you can take a snapshot with the code and it merge all these snapshots, then it will create a movie. So there is some package in the MATLAB you can use for that. So I have built this movie in the MATLAB.
Okay, thank you, sir.
Any other question from audience?
Dr. Chauhan, actually, I am seeing there is a box. So if you allow, I can explain this.
Yeah. You can.
So there is a question like kindly explain period doubling and when it occurs. So I'm talking about the period doubling. Period doubling means you are just getting double of the period from the previous one. It doesn't mean that you are getting period doubling from just from limit cycle. Maybe you are getting a period of 4, maybe you are getting period of 8, maybe you are getting period of 16. So previous one, that is called your period doubling bifurcation. So first it start with the period doubling, like from limit cycle to period 2. That's why we call it period doubling. But period doubling can be observed from different cycles, like from 4 cycle, from 8 cycle, from 16 cycle. These all are the period doubling bifurcations. And someone asked my email ID. So sir, maybe you can provide the email IDs or slide.
Yeah. Okay, sir, I will provide it.
Hmm.
Any other question from audience? So I request to everyone, please switch on your camera so that we can take a group photo. I request to everyone.
Sir, can I stop my?
Yeah, sir.
Thank you.
Thank you, sir, for your nice presentation. I request to Vikas sir, please accept the e-certificate.
Okay, thank you very much.
Thank you, sir.
So question is there, I guess.
Meaning of the same parameter, I can get period doubling bifurcation by increasing the value. Yes, of course. In the bifurcation, you have to increase the value of the parameter, because we are talking about the one parameter bifurcation. So we have to increase one parameter. Either there could be some A, B, C, some parameter in your system. So you can increase any of the parameter and you can get the bifurcation, the period doubling bifurcation. It's a sign, actually. It's a sign that you are able to get chaos in your system. So maybe you have to do more investigations to approach the chaotic dynamics.
Any other question? I think there is no question. Sir, please accept the e-certificate.
Okay, sir. Thank you very much.
Sir, certificate is visual?
Yes, yes.
Okay. Thank you, sir.
Okay, thank you very
Thank
much.
you very much.
I think I have completed on time. And,
Yeah.
Yeah.
Thank you, sir.
Thank you very much.
Sir, wonderful lecture, sir.
Oh, thank you very
Thank you
much.
so much.
Yeah, thank you.